equal to the cloud. All right, we are now being recorded. Yep, 15 minutes later, I think we got most of the things. All right, so today's lecture is going to be focusing on how to work with the call frame. So the call frame has the arguments or parameters from the perspective of the callee, the return address, and all the local variables. So that's how it's going to be structured. So one way to do this is to use an example. So I'll use an example to illustrate how this works. And I'll use a very interesting sort of, example. Let me go ahead and write the example in Notepad. I haven't used Notepad for eons because I have not used Windows for a long time too. All right. So in this case, I'm going to write the C code first, and then we'll try to convert the C code into assembly code. Okay. And it's going to have two parameters, one local variable, because I want to illustrate all of those things. So this is going to be pound include std.int.h. And I know the resolution is not going to work out very good here. So let me stop the share first and change the resolution, because it's using the maximum resolution of the monitor, which doesn't show well on the projector. The projector only has a native resolution of 1280 by 720. So this should look a lot better on the projector. And then we are going to screen share again using this screen. And it's still being recorded. Okay, so that should be okay. So is that better? I mean, can you guys view the text a little bit better? Okay. Now this classroom is kind of long instead of wide. So if you're having problem hearing me or reading stuff on the screen, just move forward a little bit. All right. So we'll continue to write this code. And we're defining a function that I'm going to say, postAdd. Okay, so uint8_t postAdd, which is kind of like a post increment, except you can specify how much to change the value of that something. And because I'm using C only, not C++, so the only way to pass a parameter and to change something is to use a pointer. So we have uint8_t, and this is going to be a pointer to the thing that is going to be incremented by a certain amount. So this is going to be a pointer to a variable. And then the other one is the amount. Okay, so how much do we want to increase this particular variable that is pointed to by p-var? So we just say amount. Okay, so that's one thing we can do. So the key of a postAdd is it has to return the value of whatever thing that p-var is pointing to prior to adding amount to it. So that means one way to do it is to use a local variable. In this case, we'll say old value, and the old value is just going to store whatever p-var has, or whatever thing that p-var is pointing to had. And then we'll add that amount to p-var. So whatever p-var has is now incremented, or we add amount to it. And then we'll just go ahead and return old value, which is the value of the unsigned 8-bit integer that p-var is pointing to, but prior to the amount being added. So are we okay so far with this code? Does everybody understand what this code is doing? All right. So this is one way to kind of look at post increment, okay? Because post increment is returning the value of the variable just prior to being added, just prior to having one added to it. All right, so in order to test this, we have to give it a main function. So we're going to have a main function here. And in the main function, we can have our own local variable in main, and we can call this x. X is initialized to some particular value, 24, for instance. And then we'll go ahead and call postAdd, and we'll have another local variable here. Let's call this y. And y is going to be postAdd, and then we have to pass the address of x, and then the amount that we are changing, let's make it a 5. Okay, there we go. And return 0. All right, so I'm going to pause here, just to see if there are any questions about the C code itself. If there are no questions about the C code, then we can go ahead and look at the assembly language implementation. So do we have any questions about the C code? Okay, no questions. Yep, go ahead.
How is it returning first, if not adding? Like, you have the add lines before the return.
I have the,
Like in the function itself,
Mhm.
you have the return after the adding thing.
yes,
But you said like it's returning first.
it's returning the value before the adding.
Oh, like the value before.
Yeah.
Not returning before.
No, because if you return first, then you have no way to execute a code after the return.
Yeah.
So I might have phrased it incorrectly. We can actually copy and paste this and get it to run in online GDB if anyone is interested. So is there any interest to see how this code works in online GDB, or you guys are all pretty comfortable with this code and we can just go straight to the assembly language translation? Any preference one way or another? Nope. Okay, all right. All right, so I'm gonna, let's see, I want to change the size of this just so that I get enough room to look at the assembly code. All right, so new window. There we go.
Sure if this is important or not, but I don't think these computers have Java installed on them either.
Oh, okay. Do you, okay, they didn't make the change to all the classrooms.
Yeah, sorry.
So that means we may not be able, okay, wait. You can all run the virtual machine remotely, so you kind of have to reinstall everything like in Ubuntu. Oh, okay, I think I got a solution. So this is for the lab portion. So in the lab portion, what you can do is to go to, what is the name of the subdomain to get to the VDI? Okay, vdi.flowsreels.edu. Once you get there, you can use VMware Horizon HTML access. Sign in, just your usual district sign in. I might have typed my, oh, okay, there we go. All right, so once you get here, you go to ARC BCS, not BCS Ubuntu, because I think the Windows version already has that installed. And if it does give you the warning, we can just go ahead and accept the risk and continue. And if anything does, anything bad does happen, we'll blame it on the district, because they are responsible to maintain all of this stuff here. I'm not sure I want to do that, but doesn't give me an option. Click OK to continue. That's the only option I got. All right, so this may work. Okay, I'm not sure whether Java is installed on the virtual machine, but if it is, then we can use this way to kind of get around the issue of the computers not having Java installed. And it's going to take a long time, so I'm going to get back to explain the program first, just having the sign in the background to continue its own work. All right, so postAdd is the key here. So we want to start this program with no op, JMPI to main, and then we have postAdd here. And postAdd is a subroutine, which means eventually it has to return. So the code to return is LDBD increment D JMPB. Now, even though I'm just using these 3 instructions without quite explaining what they do, you really should understand what they actually do. Okay, what each instruction is doing and what they're doing together, how that relates to the stack operation. and how it relates to the C concept of returning from a called subroutine to the caller. Okay, so that's something that you should know already by this time. And then we can define main. Main is going to halt at the very end. So now it's time to kind of think about, but main does have local variables, okay? Even though it's not a full subroutine, it has nowhere to return to, it does have local variables. So let's go ahead and find out, how to do that. So this time I'm going to go here to initialize the stack pointer. The stack pointer is initialized to location 256, but since we can only store 8-bit numbers, and 256 is a 9-bit number, so we can only use 0 to represent 256. So we talked about that part also, quite a while ago. Okay, so from the perspective of main, it has two local variables, x and y. So in the description, I would allocate, the local variables in a reversed way. So I will first allocate for x, and then I'll allocate for y. So x is going to have a higher address compared to y, and both of these are living on the stack. Are we doing okay so far with this? So local variables are also on the stack, and we have to allocate for that space because we need 2 bytes here. So we need to allocate 2 bytes to represent, x and y as local variables of main. Do we have any questions about this part? All right, so I'm going to use some labels here. So we'll say main underscore y is going to be 0 because after the allocation, y is going to be pointed to directly by the stack pointer. Main underscore x is going to be main underscore y 1 plus. So this 1 here has to do with the size of y, which is a unsigned 8-bit integer, and therefore it is only using 1 byte. And I'm going to have main underscore LVS. LVS stands for local variable size. So in this case, it's just going to be main underscore x 1 plus. So this is basically the total number of bytes that I need for the local variables of main. Are we doing okay so far with the labels? All right. So with all of this stuff done, now I need to do the allocation because labels are a construct that only lives within the assembler. It does not translate to any actual code. All it does is to say, hey, assembler, every time you see this name, symbolic name, it is actually just representing that particular integer. That's all a label does. But it doesn't generate any actual code. It does not affect the stack pointer in any way. It is just saying this symbolic name has that numerical value. That's all it can do. So that means the actual allocation has to be done using instructions. And the way we do that is LDIA with main underscore LDS, subtract this much from the stack pointer. This would allocate for the local variables. And then the reverse, which is the same thing, except we are adding instead of subtracting, that will deallocate the local variables. So I'm writing the program in a structured way, allocate, do whatever we need in the actual middle part of main, and then deallocate before we get to the end of main. But we're still doing okay so far with the code at this point. All right, cool. So the first thing we do is we want to store 24 to x. So we want to figure out how to do that. This is the whole idea of why we have the symbolic name of main x and main y, is to refer to these two so that I don't have to mentally keep track of the actual location of these local variables relative to where the stack pointer points to. So the first thing I do is LDIA with 24, which is the right-hand side of the assignment. And then I'll have to work with the left-hand side. So on the left-hand side, this is the first thing I need to do. So at this point, register B will contain the offset to access local variable x of main relative from what? From where the stack pointer is pointing to. So it's not going to be very helpful because at this point, B is not even an address. But if I add the stack pointer to B, then it becomes the address of local variable x of main. Do we have any questions about this portion here? that the first instruction, LDI, is only changing register B to be the number of bytes to get to X from where the stack pointer points to. So it's just an offset. But once we add the actual stack pointer to that offset, then we actually get the address of X of main. Are we good so far? Okay, all right. And then what we do is, now that we have the address of X, we are ready for the assignment operation, because after all, the assignment operation is supposed to change the value of X. So once we have the address of X, we use a store instruction to change X to 24. And this is going to be, how we get this done. Any questions at this point? So according to this code, where am I supposed to find X? What is the actual address of X if I were to run this code?
It will be 1 less than 5. Wouldn't it?
It'd be 1 more than Y, because Y is at the offset of 0. This is at 1 byte past it. But in terms of actual location on the stack, where is it located? You can actually, okay, so the stack pointer starts with 0. We decrement, what is main LVS, by the way? Main LVS as a label is just a fancy name to say what? What is the actual numerical value of main LVS? 2, exactly. So we decrement 2, we decrease the stack pointer by 2. So that means it's going to be FE in hexadecimal. And then we add back main X to basically the stack pointer. And main X is what? Main X is just a fancy name of which numerical value? 1. So you do the FF. So that means when this code runs, I'm expecting location FF to be changed to 24 in decimal or 18 in hexadecimal. Is that okay so far? So I want to check this code out, okay? I want to find out whether it is doing what it's supposed to be doing, because I want to double check, because if this is not working, I don't have any reason to go any further, because I have something to fix first. Okay, so we'll go ahead and to get this to run. All right, so on this computer, I do not have, I'm not even sure whether it has PowerShell installed, because if it does, it can potentially, so it looks like it does have PowerShell installed. But I have not gotten yeah, this is being run on this computer, but it may not have Java installed anyway. So this may not be
Luckily,
nope.
the virtual machine does have Java.
Yeah, I know. But I don't even need that. Okay, so well, do I? Shucks, I do need that. All right, so the code is running on a computer that has no Java installed, but the virtual machine is the one that has Java installed. So I'm going to have to get to the assembler. Well, the assembler I can get to in either one, but I can only run it inside the virtual machine. This is so backwards. All right, give me a push. There we go. Authenticate one more time. Yes, all the nesting and virtualization and whatnot. But we can do this. We can get this done. All right, so I only need to get to drive. Get to the assembler. Just go there. Why does it want me to sign in again? I just signed into the district. There we go. All right. So this is CISP310. Go to processor or shared. And then processor, and then the assembler. All right, so this is good, but I cannot, well, I'm not sure whether I can paste into this or not directly. That would be kind of cool. So we can check out Control A, Control C, go to the virtual machine source tab, get rid of all the stuff in column A, and then do a paste. Woohoo, that worked. Yep. So I can copy and paste across the virtual machine.
You can do it for files though, which kind of sucks.
Yeah, the
Tried
files.
copying my logic sim over, and it didn't work.
Nope, that would not work. All right, so that works, which is good. And now I need to go to the RAM file to download it. Okay, so download to CSV. And of course, it just downloads it with this kind of default name because I have not set up the browser yet. All right, and it would be pointless to set it up because it's a virtual machine. So the next time I sign in, it may not be the same virtual machine anyway. All right, so this is okay. And inside the virtual machine, I also need to get to the other tools that I need. So I need alu.circ processor. Oops, wrong key. ALU, the processor, the register bank, and also Logisim itself. And where's Logisim? Probably on the parent folder. All right, so we'll download this much first. Download. There we go. And then go to the parent folder to get to Logisim itself. Download this one too. Okay. Move to right click. Oh, scroll down, download. There we go. And then we can unzip this one. Control C. And
I think that the virtual machine is faster about downloading files than the one I'm currently running.
fascinating. All right, give me a file exploder and go to the downloads folder. And I'm just going to stash everything here. Control V. Nope. All right. Let me get back to here. Control C. And Control V. Nope, doesn't like that. Huh. Oh, or drag.
Oh, yeah, because it does it on the main version.
I see. Okay, because it doesn't. Okay, gotcha. All right. So now I got all the files in the downloads folder. We can now run it. So CMD, the command prompt, and I just need to CD to downloads. Java. Okay, just double check, make sure Java is here. Java-jar, Logisim, and then the processor. So I'm just going to run it with the processor first to make sure that it can find all the files and then save it again, because I don't want to deal with this every single time I try to run the program. So we will go to the downloads folder. and make sure that it can find all of those components. And this is looking for the ALU, select, and it's going to complain register bank, find is right here. Select, there we go. And then I have to remember to save it first, because this will also save the path to find all the components. So this time, the next time I start it again, it's not going to ask me about those things anymore. So this is good. Okay, so now I can actually do the rest of the command. So the rest of the command is to specify load, and it has to load the RAM file. So the RAM file is assembler-RAM file. I'm not sure whether it can deal with spaces within the file name. I'm gonna guess that it can. And then we specify -tty table. This will create the output instead of running the whole thing inside the GUI mode. So let me just double check. That looks good. And then we capture the output to, I'm just gonna say this is add.tsv. So now we have the TSV file done. So within the virtual machine, I go back to the browser. And then inside the browser, I have to start, have the assembler already started. So now we have to go to the trace raw data tab, go to file, go to import. And then we upload. All right, so where's the upload? It doesn't. Huh. All right. So I think it is up here. There we go. The screen is so small, it doesn't show all the buttons anymore. Then we have to go to downloads, go to add.tsv. This is the file that we're uploading. And when it uploads, we also have to specify how to import it. So the way we import it is to replace the current sheet. This is important. And then we want to use tab as a separator and turn off convert text to numbers, dates, and formulas. So those three, all three need to be changed from the default. And then we can now click import data. And we want to see if we get, this is, oh, okay, this is not good because the first line has some warning message from Java itself. Okay. I'm just thinking, can I remove this line? May not be advisable to do it because it will change the references for all of the other tabs. All right. So what we need to do is to do a, let me see if Notepad can deal with this. Add.tsv. We just have to get rid of the first line like that. Save the file again, Control S. And upload it one more time. So file, import. And then you have to click this part here to get to the top of the dialog box to get to upload. I mean, you guys don't have to do this because you can run everything in full 1080p resolution. I have to do it because I can't do that. Otherwise, you guys cannot see what's going on. All right, one more time. All right, replace current sheet, tab only, do not convert. Import data. Very good. Then we go to the analysis tab. And what we should find is in column C, we should find location FF to be changed to 18. So scroll down, keep going, keep going. Yep, we got it. All right, so it is a lot of extra steps that I have to do, but at least to get it up and running. So are we good so far? Are we convinced that we finished x equals to 24? Yes, okay. I think this has to be a record time. It took me 45 minutes to show that we can get x equals to 24 done. Even in the history of this class, this has to be a record time.
like one of those speed conversion videos where it's like comparing Python and C++ to assembly.
Yes, that video was interesting because it put assembly language programming, right next to machine code. Machine code is even harder. We did some machine code coding in this class, okay? When we looked at opcode table and tried to figure out what is X and what is YY, that's machine code, programming right there. So we did some of that too. All right, so now we can get back to this code here and also the assembly code, because we have just verified that, yes, we can get this done. Very good. So now we can try to get the second line done. So the second line is a function call. So the first thing you need to do when you look at the translation from C code into assembly code is to ask yourself what needs to be done first. So we need to call the subroutine, but before we call the subroutine, we need to push the arguments on the stack and also the return address. So that's what we need to do. We need to push the 5 and then the address of the local variable X on the stack. The 5 is easy. Load A with 5, decrement D, ST, D, A. That pushes the 5 on the stack. Easy peasy, not a problem. The second one, which is pushing the address of X, is a little bit tricky. The reason why it is a little bit tricky is because, well, most people, when we look at this code in C and C++, it seems like to get the address of something is an extra step. But in assembly language programming, you have to get to the address before you get to the content at the address. So that means getting the address of something is actually easier than getting to the value of the same thing. Okay, so the way we do this is LDIA with main underscore X, because main underscore X is the displacement or the offset from where the stack pointer points to the local variable X. Except we have a problem now, because the stack pointer is no longer pointing to the same point right after the allocation of the local variables. So what am I talking about? This is the allocation of the local variables. And since that time, we have decremented the stack pointer by 1. So that means all of those offsets are 1 off now. They are off by 1 byte. So that means this main underscore X got us close, but not quite. We have to add 1 to main underscore X to actually get to the right offset from where the stack pointer is actually pointing to at this point, because there's an extra decrement D at this point. So it's no longer where it was pointing to when we made the assumption. But after that, we just add AD, and that becomes the address. So A is now the address of X, which is what we're supposed to be pushing. So there's no LD in this case, okay? Because we do not care about the value of main underscore X at this point. We only want to get to the address of local variable X of main. So now we can push it on the stack. So decrement D, ST, DA, that's going to push the address of X on the stack. So at this point, we are ready to actually call push the return address and then continue execution in the subroutine. So we will do LDI, we can do a decrement D first, and then the LDIA with .5 plus, and then do STDA. That pushes the return address on the stack. And now we can actually continue execution in the subroutine, which is postAdd. Like so. When postAdd is done, we got 2 extra bytes sitting on the stack. They're corresponding to the 2 arguments. It is up to the caller to allocate the arguments, because they are just wasting space on the stack. So now we have 2 increment Ds to get rid of the 2 arguments that are still sitting on the stack. And now register A contains the return value of postAdd, and we have to store that into Y. So that means we have to compute the address of Y. That's a typical thing of LDI with something. I cannot use register A because at this point, register A contains the return value of postAdd. So I can use register B, I can use register C, just not register A. So I'm going to use register B for this purpose. We are supposed to store it into main Y. Add BD. Now B becomes the address of Y. And then we have a STBA. And that should store the value of the return value of postAdd into local variable Y. And then after that point, we're done. All right, so I just wrote a bunch of code. I'm not really sure whether that's working or not. So what am I going to do? Instead of implementing the actual body of postAdd, I'm just going to make postAdd return a very generic value. So I can just check whether everything is still working or not. So this is also important when you're working on your lab/assignment today, is not to don't try to get the whole thing done in one single step, okay? I would not recommend it. Probably will not stop some of you from trying. But I would recommend doing something like this. Just write a little bit of code, make sure it works, and then continue and write some more. So I go back to postAdd, and I'm just going to say, well, instead of returning the right thing, because I'm not going to do that, I'm just making it return a specific value, okay? Let's say 137. Why 137? Because that random number just popped up in my head. That's all, okay? So I'm going to copy this and paste it into the assembler. So the assembler is actually running inside Chrome of the virtual machine, which itself is using Chrome as a terminal. So get rid of this, paste it here. And this is really quite amazing. Control C and Control V works across the virtual machine, which is great. All right. And since I don't have Reefer Spider installed here, I'm just going to have to do it the old-fashioned way, which is you go to the RAM file tab and then go to File and then say Download to CSV. And this time it's going to be the same name, except it has like -1 or something like that as a part of the file name. And inside the virtual machine, I can now go back to the command line and rerun the whole thing, except this time, the file is not going to be that. It's going to be the one with a dash, in parentheses 1, because that's the second one. So we have to kind of finish this up with the rest. Like that. Press the Enter key. Okay, it ran, and we capture the log file. And then we have to go through the trouble of going back into the assembler, go to Trace Raw Data, go to File, go to Import, and go to Upload. And it is still add.tsv because I used the same file as the quote-unquote log. Click Open, change all 3 settings, replace current sheet, use tab, and do not convert. And this time, what should I be seeing? Well, X gets 24, it's still there. So I'm still expecting location FF to be changed to 18. But location FE is corresponding to local variable Y. And I'm expecting that to change to 137 or 137, or the hexadecimal representation of 137. So now, how do you do that conversion? Real quick, come on. What is 137 in hexadecimal? 89, very good. Because 8 times 16 is 128. So you have 9 remaining, and that becomes the least significant digit in hexadecimal representation. All right. So if you do not want to go through all of these steps here to double check everything, we can just look for, okay, this is FF, getting 18, and we're looking for FE to get 8, 9. And we got that. Very good. And we also want to make sure the stack is balanced, which means the stack pointer should be back to 0 by the time we get to the halt instruction. So we can keep scrolling down. and it is 0, and then the program ended at location 2B. So everything is looking good, okay? So this gives me a warm and fuzzy feeling that everything other than the actual implementation of postAdd is working the way it's supposed to. And now I can comfortably go into postAdd and perform, and write the code for postAdd. Now, if you do not have any experience of using GitHub or any revision control program like that, I would certainly save the program under a different name so that if something totally messed up, I can go back to this point of time and go like, well, at least we know everything else is working at this point. Okay, if you know how to use GitHub because that's a pretty useful way to maintain versions of your source code. Yes.
If we were to do it on the file would be .cpp.
The assembly code will be TTP ASM. Yeah, it's just an extension. GitHub doesn't really care about extensions. Yeah. All right, cool. So what we're going to do now is to go back to the source code in C and go back to the source code in assembly language. Now our focus is what do we do inside postAdd? So postAdd is right here. As usual, the most important thing is to understand what is on the stack. So what is on the stack here will be the two parameters sitting at the higher addresses. AMT is going to be the highest of the addresses. So I'm going to say highest here. The next one down is going to be pvar. And then we have the return address. And then we have the local variable old value. So this is how the stack of the call frame is supposed to look like when everything is fully allocated. So instead of having me to remember, oh, the stack pointer is supposed to point to the old value, and then pvar is 2 bytes past that, and the AMT is 3 bytes past where the stack pointer points to, and have all of those things remembered in my head, I'm going to define labels, okay? And that's why symbolic names is useful. So I'm going to say, postAdd, or if I don't want to write everything full name, I can use PA as postAdd. So old value is going to have an offset of 0 because after allocation, that's where I'm going to expect the old value to be at, is right where the stack pointer is pointing to. PA underscore LVS. LVS is going to be PA old value 1 plus. So this one is corresponding to the size of old value. Old value is an 8-bit unsigned integer. It only takes up 1 byte, and therefore we have a 1 here. So LVS, once again, is local variable size. It tells me the number of bytes that I need to allocate for all the local variables. It is handy to have because I need this to allocate and I also need this to deallocate. So that's why having a label to represent the number of bytes that I need to reserve for local variables is useful, okay? So now I can do the allocation and then the deallocation. So I can do LDIB with PA LVS, subtract this much from the stack pointer to allocate. And then I will also do about the same thing to deallocate, except this time I'm going to be adding. So in between, okay, in between these two blocks of code, I can now say, okay, we got everything on the stack, and they are now at the right offset, compared to how the labels are going to be defined. But I'm not quite done with all the labels, because at this point, we also want to define where we can find pvar. So pvar is going to be PA LVS 1 plus. This 1 plus here has to do with the return address is taking up 1 byte on the stack as well. So after we look at all the local variables, we also have the return address. I don't need to create a label for the return address because there's no reason for a callee to directly change the return address, unless you want to hack a program. So you want to change the return point to some place that you're not supposed to go to. But other than that, there's no reason to change the return point. So I just need to get back to the parameters. And then the next one is PA underscore AMT, the amount, which is PA P var 1 plus. So this one here has to do with P var being a pointer is only using 1 byte in Textoid processor. So now that I got all of these labels defined, I can now work with these 3 statements. The first one is, well, on the right-hand side, I need to get to whatever P var is pointing to. Okay, let's see if we can do that. Okay, so we want to get to whatever P var is pointing to, LDIA with PA P var. This is the displacement. This is the address of P var. This is the value of P var. And this is what P var is pointing to. I intentionally did not put in the comments because I want you guys to do it. Okay, so after this class, after the lecture, I will upload this code so that you guys can, have the source code, and then you can also, add your own comment to the source code. And then after that, I got the right-hand side already. Now we need to focus on the left-hand side, which is just, okay, we just need to store all this stuff to old value, which is my local variable. But the way we access a local variable is the same as the way we access a parameter. The only change is how far is it away from the stack pointer? One is on one side of the return address, lower than the return address. The other ones will be on the other side of the return address, meaning they have addresses that are higher than the return address. But other than that, they're all on the stack, okay? And I have defined the offsets to actually access each one of those. So the method to get to old value is pretty much the same. LDIB with PA underscore old value. Add BD, oops, typo. And then we say STBA. Because at this point, register A already has the right-hand side. Register B has the address of the left-hand side of the assignment. So that will accomplish this particular assignment statement. The next one is to add AMT, the amount, to whatever P var is pointing to. So if I want to optimize this code, I can say, well, this is the same thing as that thing here. So I could have saved that in a register. So I don't have to recompute everything. Well, I mean, it's not a big deal. Okay, so we'll go ahead and not to optimize this code and just recompute everything. So LDIA with PAAMT, this is the offset to amount. This is the address of amount. This is the amount. So register A now has the right-hand side, and now I have to deal with register B being the left-hand side. So LDIB PA P var, that's the offset to P var. That is the address of P var. This is P var itself. And now we are storing to whatever P var is pointing to. All right, and all of this is done. So what is left for us to do is to return the old value. So that is just LDIA with PA old value, add AD, LDAA, and we're done. That should do it. So do we have any questions about this code? Questions? Okay. Well, let's see if it works. I really have no idea whether this works or not because I came up with this example program just this morning after I get everything else fixed. Oh, that is not it, isn't it? All right. So what did I miss? Control A, Control C. Go to here, Control V. There we go. All right. So what do we expect to see this time? Okay, this is important because now I have the entire code implemented. So we want to look at the C code and see what it is supposed to do. X has a value of 24. Okay, that does not change, except postAdd will add 5 to X. So that means X will end up having a value of 29, which is 1D because it's 16 plus 13 and D is 13. So it's going to be 1D. So X or location FF should become 1D. Location Y would get the old value of X, which is 1,8. So location FE would become 1,8. Location FF would become 1D. So that's what I'm predicting the program should do, okay, in terms of what we can easily verify. So now we can see if the program does what it's supposed to. So we will double check, make sure that we don't have any errors. Okay, so there are no errors in column B, which is good. Very good. And we go to the usual stuff, go to RAM file, go to file, and then go to download CSV. And then we can switch back to the command line in the virtual machine. And this time we have a file name that has a 2 in it. Okay. And then we just run the code again, capture the output using the same file name, which is add.tsv. Go back to the assembler, go back to trace raw data. And oh, this part does not seem to affect it at all. Okay, that's nice to know. So we do another import. And we want to get up here, go to upload, go to add.tsv. Specify the 3 things that we have to do. Replace current sheet. Separator is a tab. Do not convert. Import data. And then we go to the analysis tab and see if it is working or not. So if you want to shortcut everything, you can just highlight column C and then go to find and replace, Control H. And you can just look for, asterisk FF equals 2, because this will, okay, this is really cool. Instead of locating just FF, I can ask it to locate if there's any change to FE or FF, look for that, okay? So to do that, you can use regular expression. So regular expression is right here. You just have to check, to search using regular expression. But when you use regular expression, the asterisk symbol has a special meaning. So that means if asterisk is what you're looking for, you have to escape it with a backslash. And then we have a F. And then this is where you can specify E or F in square brackets. So whatever you specify in square brackets are alternatives for one single character. So in this case, I'm expecting either an E or an F followed by, following the first F. Okay, so this is regular expression. It's really quite useful. It might take you a little bit of time to kind of learn it and get used to it, but it's worth that time. Okay, it's good investment. All right, so that's all we're looking for. And of course, I have to get to the bottom of the screen to get to find. So the first thing you found was FF is getting 5. That would not be right. That would not be right. Okay, so it's missing something. 5 was the argument pushing. We push 5 on the stack, but that's not the right place. In other words, it is not reserving the space for the local variables. So I can stop right now because I know this is not what I'm supposed to be seeing. All right, so if this is not what I'm supposed to be seeing, let's go back and see what is going on here. Okay, this is already inside the subroutine. Now, how do I, all right, so this is a question I want you guys to answer. How do I know that this is already inside the subroutine? In other words, the problem is within the subroutine itself, but how do I know that? I know exactly what I forgot to do, but I'm not going to tell you yet why, what I just forgot to do. It's pretty obvious, okay, to me at least. But the first question is, how do I know we are inside the subroutine? This is not main. Main did not do something wrong. We're inside the subroutine right now. How do we know? What do all the columns represent in this case? There are two ways for you to find out that we are in the subroutine right now, or which line we are located at. So the new feature of this analysis tab is we got column F to tell us what is the line number, and then column G will give us the actual line of the line number. So this is telling me that on line 33, this particular ST instruction is what is putting the 05 into location FF. All right. So where is line 33? How do I find out where line 33 is? We can go back to source, right? Go to the source tab and then just go to row 33, right? Right here. And then we just look this up and go like, where is this located? This is actually inside the subroutine already. This is actually inside postAdd. Okay, so postAdd is putting 5, which is the amount, into whatever P bar is pointing to. That's because I forgot to add it to whatever P bar is already pointing to. It's supposed to be an increment at plus equal to. My code is doing just an equal to. Okay, so that's why it's not working. But the rest of this program should still be working, which means if I do another control H, oh, okay, forgot the previous one that I'm looking for. So if I look at location FE, it should still be updated to 18. Yep, so that part is still working. So the only problem that I got with this code is just what I mentioned. Let me go back to the C code and show you what the mistake was. So instead of doing this plus equal to, it's just doing this. And that's why we saw X being changed to 5, because it's really just storing the amount and not incrementing increase by the amount. Okay, so I can now go back to the source code and try to fix that. Since I did not leave behind any comment, so now I have to actually go find out, which line is supposed to do this, right? So that would be, well, we are changing whatever P var is pointing to. So I'm gonna say it is this part here. All right, so we got amount, and we need to add to whatever P var has. So that means we need to retrieve here, whatever P var has, add whatever amount is, which is already in register A, and then store register A back to this place over here. So that means what I need is LDCB add AC, and that should fix it. So in terms of the new code that I added, load CB is going to load whatever B is pointing to into register C. That would be the value that P bar is pointing to. So C is representing whatever P bar is pointing to. A is representing the amount. So I'm adding whatever P bar is pointing to amount. Okay, we got the sum, and then we just have to store the sum to whatever B is pointing to, because all this time B is still P bar. So I'm storing to whatever P bar is pointing to. And yes, I did not add any comments, because that would be a good exercise for you guys to do. I will upload this code, okay, so that you guys can use it as an exercise. So let me double check, okay? So we want to rerun this whole thing, make sure that it is correct this time. So Control A, Control C, go here, get out of the search thingy, go to source, get rid of the whole column, paste again, go to the RAM file tab, wait until it's done, go to file, download, CSV, go back to the command prompt. I kept using the control tab, alt tab, which doesn't work inside the virtual machine. That works. So now I know this is 3, I think. Run the code, capture the output, go back to the assembler, go to trace raw data, file, import, upload, add.tsv, click OK. Replace current sheet, use tab only, do not convert, import. Go to analysis. And let's go all the way back to the first row. And then do the search, Control H. And then we want to specify backslash asterisk F, and then in brackets EF equals 2. And we do want to turn on search using regular expression. And go find. All right, so this is in main. This is the first time we put 24 in X. And this is that the same thing? Okay, this is row 150. Let me just double check. All right, so find. This is the next time it's updated on line 210. It did not store the sum. Okay. Oh, it's a single equal to, not double equal. So these are read operations, they're not write operations. I want to focus on just write operation. So I want to focus on specific range, which is just column B. It means column C. So there we go, column C. All right, so that should be better. Find again. All right, so this is the initialization. It 5 is added to X inside the subroutine. And this is Y getting updated by the return value of the subroutine. So it's all doing everything correctly at this point. And we just want to make sure that stack pointer is 0, 0 by the time we get to the halt instruction. And everything is working correctly then. All right. And just in time too, okay, this is the end of the lecture. So your lab has 2 components. Let me show you what your lab looks like at this point. And I will upload this code because I think it's super important that you guys have access to this code. So let me get to, what is the best way to get there? Okay, single sign in, go to Canvas, okay, this way. And it wants me to sign in again. Alrighty, so this is the Tuesday, Thursday class. All right, so you got 2 lab activities that are assigned today. One is called call frame, and one is called function calls. Function calls is going to have a program that you have to write that you probably cannot be done by today's, by the end of today's lab time. So that one is due 1 week from today. So you do have 1 week to finish the actual coding, which is going to be collected by function call program submission. So you have all of these components. This one has a access code. So call frame has an access code of framed. So I'm gonna write it on the whiteboard. Framed is one. And then the other one also has an access code. And it is swap. Here you go. I think both are visible to you now. If you refresh your browser, you should be able to get to see both of those. And if you want to run Logisim, you're going to have to do it the way that I did in today's class. So you're going to have to re-download all those files, to a folder on inside the virtual machine, and then double-click on logisim310.jar to run it in GUI mode. If you don't want to run it in GUI mode and you want to run it in command line mode, this is the way to do it. All right, so do we have any questions before I stop the recording in Zoom? And then I will share that link with all of you. So if you want to, kind of refer back to the content of this class, you can. Do we have any questions? No questions? All right, so I do have one more thing to say, okay, is how do you study for this class? The way you study for this class at this point is not just about reading, it is about commenting the code and understanding the connection between the concepts. So what I mean by that is you have to look at this code here. I know many of you are already in here. I would suggest you to make a snapshot, okay, but that's just me. I will give you the source code as well. So this way, if you don't get a snapshot, you can actually just run the whole thing again and then have your own snapshot to record. The first thing I would do is to go to the source tab and try to understand what each line is doing and comment it accordingly. Now, what do I mean by that? I will look at each line and, for instance, this line here, what is it doing? What is PALVS? What is the significance of PALVS? So this is not just about figuring out that LVS is 1, okay? Because knowing the label is defined to be 1 doesn't give you any connection to the concepts that we are talking about. So you have to understand that this is the size of all the local variables. And why is that important? Why do we know how many bytes do we need to allocate for all the local variables? Because the subroutine, the callee, has to make that allocation and also have to make the deallocation. So this way I can refer to just this label name in order to allocate and also to deallocate. That's the significance. And I can also just point to one instruction here and go like, okay, what is this doing? If you just say that we are going to change register A with whatever register A is pointing to in RAM, that is technically correct, but it's not very helpful because you're explaining the mechanism of the instruction itself without any connection to the concepts that we are focusing on at this point. What concept are we talking about, TAC? We are focusing on how this is relating to the C code. So that means you have to look at this line here and be able to answer and go like, okay, I know what A is in the context of the C code that we are working with, which I am not sure where it is. Okay, it's right here. So you have to look at the source code in C and look at each line of assembly, and you understand, okay, by this time, register A has this thing in the context of the C code. And that thing, most likely, is something that is on the stack. So you also have to make connections to how the stack is organized and how the stack is holding things that are relevant in the C code. So you have to make all of those connections and comment this program, with all of those insights that you have, as you read this code. So that's one. The second thing is I would print out the analysis tab, okay? You can get rid of all the empty lines. You can copy and paste this entire thing into Excel, clean it up a little bit, format it the way you want, and then print it out. After you print it out, you can also, kind of look into each and every single instruction that executes here and find out what exactly is this instruction doing in the context of the runtime behavior of the program, and then make all those connections again, okay? This instruction here is connected to that statement over there in the C code. This register contains this concept in the C code, and so on. And I would do this to every single instruction of the entire program. Okay, some of those would be very redundant because it's the same mechanism, the same at least 2 instructions to get to the address of something. So by the time you say, this is boring, I don't need to comment this anymore, fine, don't comment. But there are still a lot of tricks, okay? I wouldn't say tricks, but there are a lot of techniques in this particular program that you want to kind of comment and make all of those connections. The more you do at this point to comment, to kind of make all the connections, and to write a note on the side of your own understanding of what is going on, how to translate a program into C code, the more prepared you are for the final exam. Because the final exam is going to be paper only, which means everything, all the note that you're taking, whether it's electronic or on a piece of paper, you can bring that with you on the in the final exam. So all of this, quote unquote, studying, commenting, and whatnot is really designed to help you, get ready for the final exam. All right, so I'm not going to yak anymore unless you guys have questions. If not, I am going to stop the recording and give you a link to the recording of today's lecture. It's going to be a Zoom link, but I think I can manage to get that part done. And then you can get started with your lab activity today. There's a piece that is due in a week. I would definitely not procrastinate because it looks simpler than it is. So it's gonna take up some time to try to figure that part out. All right, I don't see any questions. So I'm gonna stop the sharing, and also just a mild reminder that I do have office hour before class on Tuesdays and Thursdays. And so far with this class, I have had maybe 2 visits. So if you're having trouble understanding the concepts, you have that resource available to you, which is right before class. All right, I'm gonna stop the recording and also the screen share.